to the 16th lecture of Engineering 1170. I actually don't know if it's the 16th lecture, but whatever it is. So today I want to do a quick review of the stuff that you said last time was confusing. There is no doubt about this being confusing. There's also no doubt I can possibly tell you enough so that you can hold it all together in your head and make it totally not confusing. I've discussed this with several professors, and it's just this problem. And the problem is that there are simple mechanics kinds of problems that you can do with simple formulas, but to really understand those formulas involves more advanced things than I can cover here. Nonetheless, I think I'm hoping that I can tell you enough so that you can feel comfortable with some of it and at least know what you have to be careful about. Okay, so I want to do this review. I want to do the homework problem, the second homework problem. I just want to do it for you. I want to do it for you a few different ways. And then I want to talk about some things which I know are confusing to some people, for example, units. And then I want to move on to a topic which properly belongs in the math 2930, which is ordinary differential equations, but you can understand the basic ideas and learn to get around with differential equations in MATLAB with the skills that you now have. Okay. Let's start with check in here. Take out your clickers. And let's just for the fun of it, let's do a vote on something or other. How much time did you spend on this homework that includes the quiz, redoing the quiz, and the problem 2? You spent more than 8 hours, 6 to 8 hours, 4 to 6 hours, less than 4 hours. More than 8, 6 to 8, 4 to 6, less than 4. Okay, so we're doing, I would say it's about like homework should be. You're supposed to be working about 60 hours a week at school. You should be taking about 15 credits. So that's about 4 hours per credit. This is 3 credits. Should be 12 hours, but you're in the class for 2 of them, and you're in the lab for 2 of them, so there's 8 hours left. And you have to think about life and write lab reports, so it should come out like 6 to 8 hours for the homework per week. Right? Anybody disagree with my arithmetic? That leaves you 68 hours to sleep, eat, and so on. Facebook. Okay. So for any system, any collection of atoms, any machine, any human body, any horse, any bicycle, any person with a bicycle, any part of the bicycle, any collection of bicycle parts, anything you want to call your system, we have some basic laws which we think are true. And perhaps the 2 most important basic laws what's most basic? Conservation of mass is maybe more basic, but the ones that you work with in engineering, perhaps these are the most 2 important ones. So we have linear momentum balance, LMB, linear momentum balance, and it says you look at all the forces on a system and it tells you how much, on average, the system accelerates. And when you say on average, sometimes that means like a vague statement, but this means precise average. The precise average motion, what do you mean by the precise average motion, is you take every little bit of mass and look at its acceleration, add up all the masses times the acceleration and divide by the total mass. And then you multiply by the total mass to get the average mass times acceleration. And this precise quantity, what do I mean by precise? Precise, like in engineering practice, 1 part in a billion. So if you're willing to think, I don't need to calculate any more accurately than 1 part in a billion, you can think of this as precise. Maybe 10 billion sometimes. Maybe if you're doing things that are moving very fast and relativity is important, it might only be 100 million, but on the order of 1 part in a billion. Precise. This one mathematically leads to this one, which is you look at the total force and you look at the velocity of the center of mass, and it tells you the rate of change of not the kinetic energy of the system, but part of the kinetic energy of the system. This is not the whole kinetic energy of the system because, for example, if I were floating in space and still in front of you and wiggling my body around, I would have kinetic energy, but my center of mass would have no motion, and this term would be 0. So this is only part of the kinetic energy. On the other hand, if we look at the whole energy budget, you have that the energy flow into a system is equal to the rate of change of energy in the system. How can energy flow into the system? One way of looking at things is energy can only flow in the system two ways. One is by something called work, and the other is something called heat conduction. And this work can include electrical work, it can include mechanical work, force times velocity, it can include chemical potential work. In this class, this is the main thing, the mechanical work. And the mechanical work has to do with the force times the velocity, not the velocity of the center of mass, but the velocity of the point in the system where the force is being applied. So when we apply this to, on the right-hand side, we have the rate of change of kinetic energy, which has two parts, of total energy, which is two parts. One is the kinetic energy, which has the center of mass part and the relative to center of mass part. And then there are other terms, like the heat and the chemical potential and the spring stretching and so on. Now, why this is confusing, say, for the bicycle, is the bicycle accelerates. You're on the bicycle, it accelerates. Why does it accelerate? Because there's a force pushing it forward. Where's the force pushing it forward? Where does it come from? Well, you think, it comes from me. I'm pushing on the pedal. But where does it come from? Looking at the system, the bicycle in person is a closed system. What force is acting on that system? It's a force from the ground on the bicycle tire. The bottom of the tire has 0 velocity. Therefore, this work term, when you're pedaling a bicycle, is 0. So when we apply the energy equation, this side is 0. Now it's tempting to use this equation, and correct to use this equation, but this equation isn't about work, it's a momentum equation that happens to have dimensions of energy. So this is not the first law of thermodynamics, because if we look at the force, this force times this velocity looks like it has dimensions of power. It does have dimensions of power, but it's not the power of the force in the system, because the power of the force in the system we see is 0. So how does the energy balance go for a bicycle? Is that some internal energy, chemical energy, is being turned into kinetic energy. Okay. Any questions about that? Yes?
So the way of thinking about the problem is like different between linear momentum balance and thermodynamics, but like to get to the answer in time, it's the same calculation.
That's the problem with this, is that the formulas are all simple, and even if your thinking is all wrong, you'll still get the right answer. There's another way to think about it, which is maybe more accurate, which is the following. When somebody says a bicycle rider has half a horsepower, or a car has 100 horsepower, what do they mean by that? Well, you could say what they mean by it is something about the first law of thermodynamics, and there's these different accounts in the energy, and they're moving from one account to another account, the internal energy. Or you could say, well, the person who said that isn't thinking so carefully. And what they mean when they say the bicycle rider has 25 horsepower, no, the bicycle rider has half a horsepower, or the car has 100 horsepower, is they mean that from somewhere, the chemical gods, there has been a gift to the mechanical energy department of 25 horsepower. Which means what you're saying when you say a car engine has 25 horsepower, or 100 horsepower, I keep changing my mind. Let's say 25 horsepower. Car engine has 25 horsepower, that the kinetic energy of the car is increasing at a rate of 25 horsepower, plus the work that the car is doing on the environment, those two together is 25 horsepower. So it means there's a gift from the chemical gods to the mechanical work accounting department of 25 horsepower. And don't worry about whether it's momentum or thermodynamics or what, there's just this available mechanical term. Okay, so let's take it that way, and let's do this bicycle rider problem. So the bicycle has 0.5 horsepower. Is that reasonable? Not reasonable. Okay, so one thing I would like you to get out of this course, or if you don't get out of this course, one thing you should have, or one thing you should work on having after this class, is some sense of some numbers. right? What distinguishes an engineer from a philosopher or a physicist is you've got to have some sense of the real world. Of course, you can plug things into Google and into your calculator, and you can do the calculation later, but you'd like to have some sense of numbers. So let's just talk about, say, the human bicycle rider, and talk about human power. And the question is, what is a reasonable amount of power to expect to get out of a person? Does anybody know any numbers having to do with human power? Nobody here's on the crew team? Anybody here use a Concept 2 ergometer? Rowing machine? Anybody use a bicycle machine that's got a meter on it? Anybody do a height? Do you remember a number? Anybody in high school do an experiment where you ran up the stairs and you looked at the change in potential energy and you timed the difference and so on? Do you remember any numbers?
I remember they were around like under 1.
What?
They were under 1.
Under 1 what?
Under horsepower. Pretty sure.
Watt, horsepower,
Horsepower.
foot-pound, inches per second, under 1. Okay, so how much power do you have available? This is an experiment you can do for yourself. How can you do it? Go to some big staircase, measure the height of the staircase, see how much potential energy you can gain running up the stairs and how much time. Look at your weight. The weight times the height is the energy per unit time, is the power, and you can see what your power is. How's it going to work out is that you can make a plot, and the plot has in it the duration and the power, and you can measure the power. Some reasonable way of measuring power is, say, in watts. So we can do power in watts. And what can somebody do? So I'd like you to remember some numbers, or have some sense of the numbers. One number to remember is way down here at the time scale of like 5 to 20 seconds. How much power can you get out of a person? Anybody want to make a guess about this? Let's say an athlete. You take an athlete, you ask them to run up the stairs as fast as they can. Big football player. Or you ask them on a rowing machine to row as hard as they can. Or you put them on a bicycle machine. Anybody, any guesses about this number? In watts or horsepower or anything? Yeah? 90 watts. Yeah? Say again? 0.3 horsepower. I think almost everybody in this room can get pretty close to 1 horsepower on this short time scale. And good people can get up to about 2 horsepower. So one thing to notice is we don't want to know what is a horsepower. And this is something you can look up. It's 743 watts. Is that right? 743? Does anybody remember from their Google searches last night? Yes?
746.
746. It's 745 point something or other. I think that's right. Okay, now who knows what a watt is? So somewhere you should know what a watt is. Well, a watt is a unit of power. Power is energy per unit time. A watt is a joule per second. Basically, by the way, you should know all the numbers I'm going to write down today. Everyone in the room should know all of these numbers. Modulo an error of 0.5% or so. Okay, what is a joule? What's a joule? Who does not know what a joule is? No, who knows what a joule is? Let's be positive here. Who knows what a joule is? A joule is a unit of energy. Energy is force times distance. What's a force? Force you usually associate with mass times acceleration. We want to do this whole thing in SI, so the unit of mass is kilograms. The unit of acceleration is meters per second squared. And then we've got to multiply that by meters. So 1 joule is 1 meter squared kilogram per second squared, which you read as a kilogram times a meter per second squared times a meter. Now if I take a thing which has a mass of a kilogram, Say I take a thing which has a mass of 5 kilograms, and I raise it 1 meter per second. What's the power involved? 5 kilograms being raised 1 meter per second. 5 kilograms being raised 1 meter per second. How many people say 5 watts? How many people think it's something different from that? What do you think it is? What? Say again? I think so too. 50 watts. Why is that? I'm raising this 1 meter per second. It's force times velocity. What's the force of 5 kilograms? It's 50 newtons because the gravity acceleration is 10 meters per second squared. It's 9.8, big deal. 10, call it 10. So there's a force, 5 kilograms, there's a force of 50 newtons. 50 newtons times 1 meter per second is 50 watts. Okay, so what's the number here? In this time scale, we can get on the order of, let me put here, 1,500, 750. We can get somewhere, I'll just put an error bar in here, between top athletes and sort of normal people, something like that. Then let's talk about long duration. Long duration is, say, something like 8 hours. And the standard number people put out is over here. I'm going to put, here's 75 watts, and here's, say, 150 watts. And this is going to be the difference between a more or less normal person and a pretty good athlete. What you can do. And then in between, there's some curve like this. And so maybe this would be sort of an average person would be something like that. So this is sort of the athletes. What are some examples on this high curve where people really care about this thing is for human-powered airplanes. They barely work, these human-powered airplanes, and the people flying these planes for a few hours are able to do something on the order of 200 to 300 watts for a few hours. They're somewhere like this. Now they're light people, so a football player might do better, but football players aren't endurance athletes, so I don't really know how it works out for big people trying to work as hard as they can. But these light people powering human-powered airplanes, and that isn't supposed to be 750, that should be something like 300 watts. But the number to remember, if you would say one number to remember, is this number right here. And this is 100 watts. And this is about, if you take a person who's working, and they're just a regular worker, but they're doing real work, they can do something like 100 watts all day long. I'm going to get to the bike problem, but I tell you a side story. Probably once or twice a year, I get an email from somebody who has a business idea and they want to consult with me about this business. And the business idea is, there's a big fitness craze in America. People are going to all these health clubs. They're running all these machines in the health clubs. What a waste of energy. Why don't we take those machines, the elliptical trainer and the rowing machine and the bicycle thing and the treadmill, and connect them to generators and make electricity so people are actually doing something useful rather than the health club. Okay, now is that a good idea? Well, let's just look at it from an economic point of view. How much does a machine, a good machine in a health club cost? $2,000. Let's say we got to modify that machine to make it so it works well with an electrical generator, and we have to build an infrastructure with it so that we can plug it into the electrical grid so we can get useful electricity out of it. So say $5,000, I can make a good, robust, human energy harvesting machine. Now how much energy can we get out of a person? About 100 watts. How much does electricity cost in America today? Does anybody know? Does one person know how much electricity costs in America today? Yeah? Say again?
19 cents per kilowatt hour.
Where's that? That's high. What?
With taxes.
With taxes. I think the usual number is 10 to 12 cents a kilowatt hour. So you have to pay per unit energy. A watt is the unit of power. Power times time is energy. When the people bill, they say 10 cents per kilowatt, but that's like sloppy language, is per kilowatt hour. So it's about 10 cents per kilowatt hour. So the value of the electricity that a person could make, working pretty hard, is about 1 cent per hour. So you run the health club 10 hours, say, because it's open for 14 hours, but there's lag time. So you get about 10 cents per machine per day. Or if you run the machine for 300 days in a year, then you get $30 of electricity in the year, and you pay for the machine in just 160 years. Okay, that's how it works out. Any questions about that calculation? So it doesn't work out so good. Now, it might be a good idea because it might teach people about what energy is all about and how ridiculously cheap energy is, that you think you're doing a lot when you're running around or pedaling a machine or so on, and you really steal it from the under the ground for only a penny an hour. That's what your work is worth, is a penny an hour. Okay, so now we've got this power. We've got this bicycle rider. I say we can do a half horsepower if we're working really hard, trying to accelerate the bicycle, and we'd like to figure out what's going on with this bicycle problem. So for this bike, our first model of the bicycle is that the power is constant. Now it's a lousy model of a bicycle, and we'll see why it's a lousy model, but roughly speaking, you think, okay, let's start out with power being constant. And what do we mean by power? We mean that which is going from the chemical gods to down here to our mechanical accounting department. Let's assume that all the kinetic energy is equal to 1/2 times the mass times the v squared. Now that's not exactly right, because there's kinetic energy in the leg spinning around, there's kinetic energy in the wheel spinning around, there's kinetic energy in the chain moving, but we make the approximation that this is true. So when we take our equation saying that power is given to us, what we have is that the power which is given to us is d by dt of 1/2 of mv squared. So if you want to start this problem and say, what's the basic equation we're given, this is the equation we're given. This is where all this thermodynamics takes us. Now, the mass is constant, we'd like to think, over the time scale of this experiment. And then we have to differentiate this. We use the product rule of differentiation, or the chain rule of differentiation, and this turns into m times v dot, where dot means the time derivative. Now we want to figure out what v is as a function of time, and we have this thing, we have this equation where we have these constants which are given to us, which are the mass, and we said let's assume the power is constant, and we want to figure out what function of time is velocity so that this equation is always true. And that's basically what your homework problem was. And now I want to talk about a few different ways of solving this problem. So we're going to we're given this, and we're given that we're starting from stop, so we're interested in v of t is equal to what, given that we're starting from stop, and given that v at time equals 0 is equal to 0. Okay. Now how are we going to solve this equation? So let me show you what is really the method. Okay, really the way problems like this are solved is they're solved on the computer, and that's where we're going to go in this lecture. Now exactly this problem, is it solved on a computer? Probably not, because this only comes up in homework problems, and it happens to be one we can do with pencil and paper 5 different ways. But in general, you're stuck with some weird equation like this. We're going to hack our way through on the computer to do it. Before I get to that, I want to show you the classical pencil and paper methods. Now this thing is called a differential equation. This is called an ordinary differential equation. What does that mean? It means that we have an equation and it has derivatives in it. An equation that has derivatives in it is a differential equation. That's the meaning of the word differential equation. It's called an ordinary differential equation because it only has ordinary derivatives. It doesn't have partial derivatives. It doesn't have things to do with gradients and so on, the stuff from Math 192. It's only got ordinary derivatives. So this thing is called an ordinary differential equation, and the big acronym for that is ODE, ordinary differential equation. Now, how do you solve the ordinary differential equations? Well, like I just said, the real way that real people solve real differential equations in this millennia is they solve them on the computer. But some simple ones you can solve with pencil and paper. Now, how do you solve ordinary differential equations with pencil and paper? And there's one main method which works better than all other methods, and it is the dominant method. And people will try to fool you into thinking that what I'm saying is not true, but what I'm saying is true. And here's the method. Anyone want to guess on the method? Anoop, do you know what the method is? What? No, it's not computer. Let's say we're in our MacGyver mode, and we've got to get through this, and we don't have a computer. Yeah? Separation of variables. Separation of variables works sometimes. It will work for this problem, whatever you mean by that. How do you know that? Are you in 293 now? I see. Yes, Anoop?
Yes.
Guessing. That's the method. This is what's worked for you on exams and homework, and it is the method by which real professionals solve differential equations. You guess. Now, how does guessing work in homework? If you just say, just guess the answer, you can look in the back of the book, and if you can see it's there, then you say, oh, I guessed right, and then you write it down, but then it just looks like you copied from the back of the book. And if it's not in the back of the book, you guess, and you said, here's my guess. Right or wrong, I don't know, I just guessed. Well, the thing about the method of guessing in differential equations is that you are given the tools to check your guess. So if you like, it's not just guessing, it's successive guessing or iterative guessing. And it's not iterative in the sense of finding the roots with the numerical methods. It's iterative in the sense that the guess is wrong and you got to fix it. You guess again. So method one for solving this differential equation, and just when you take Math 293, keep your eyes on it. They will fool you into thinking that there are all these methods for solving differential equations. But just watch the ball and you'll see that basically there's one method, and it's called guessing. Okay? And so, what do you mean guessing? What guess? Well, you can just guess whatever you want. You're free to guess. There's nothing wrong. If your guess is wrong, it's wrong. So let's just say, let's just start out with guessing. And we'll just put one guess in here. And let's see, this thing is well, starting from stop, it's got to be going faster and faster, but it's not going a lot faster, and it's curved sort of, I don't know, must be log function. And so v is equal to a plus b log t. That feels like the right answer to me. You say, where'd you get that guess? And I say, well, I'm the professor, you're the student, I make good guesses. So you say, is this a good guess? Let's plug it in. Let's see if it's a good guess. So what you want to check the guess. And the way you check the guess is you say, I go back to my differential equation. And my differential equation, I'll just leave it the way I had it, which was p is a constant, is m times v times dv dt. That was my differential equation. And I want to see, is this equation satisfied? Now, the way equations are satisfied, different things get satisfaction in different ways. The way equations get satisfied is when their right side is equal to their left side. Then they say, it feels good. Okay, so you want to satisfy this differential equation. And we have this p, which is a constant. This m is a constant. We have this v, which is a plus b log t. I don't know what a and b are yet. So I'm going to refine my guess by picking a and b to make this work. And then I've got this, this function of time times dv dt. Now what's the derivative of log of t? Is 1 over t, so we have a b, so we multiply this by b divided by t. And now this m and p are constants, And I say this is a fine guess so long as the right side of the equation equals the left side of the equation. And can I make the right side of this equation look like the left side of the equation? By picking A and B appropriately. Can you see how to satisfy this equation? It's just looking for satisfaction. Can you pick A and B to make it satisfied? I can only see one way to satisfy this equation.
Making A0 B1.
The only way I can see to satisfy this equation is to hope that they gave me a very weak bicycle rider and said B equal to 0. It's a very satisfying equation, 0 equals 0. Okay, so it's not a good guess. I'm the professor, you're the student, I make a bad guess anyway. So this is a bad guess. It just doesn't, I can't make this work. Okay, so it's a bad guess. So so that's the way you solve the problem. You make a guess, and it's a bad guess. And that's the way that engineering is done and science is done, and the progress of society is dependent on exactly this method. In fact, this is the method that God chose for making species better and so on, is you guess and you throw out the bad guesses. It's called evolution, theory of evolution. You learn it in the biology class. You make guesses and you throw out the bad ones. So let's try the theory of evolution again. Let's put a little mutation in here, if you like. A random mutation. Most mutations are deleterious, like that one. Let's hope that we get a good one. So we want to make another guess. Guess 2. Any other guesses? What? Well, square root of t, that's a very good guess, right? Now, that's just too inspired. So you don't want, I mean, it's a good guess. But you can't hope to make such good guesses. So the way the method of guessing works is you give yourself a little freedom in the guess. So square root, turns out that's the answer to this question, right? Some of you know that. But that's like going backwards after you already know the answer. But let's just make a more general kind of guess. And the more general kind of guess that I would like to make is I say V equals A t to the n. So I don't know whether it's going to be square root or the third power or the 1/3 power. I can't see that far ahead. So I'm going to make a sort of general guess and see, can I pick A and N so that this is a good guess? So that's the nature of the guessing, is you don't guess all the way because then that's too hard. That's hoping for too much. You try to just guess in the neighborhood. Okay, so let's make this guess. How does that work? We're going to check the guess. And when we check the guess, we have to see that the power is equal to the mass times the velocity times v dot. This is p over m. Let's just keep the constants on one side. I'm going to have a t to the n. And now I've got to take the time derivative of this, which is n times t to the n minus 1, n t to the n minus 1. And then I do some manipulation here, and it's a times n times t to the 2n minus 1. And then I can take more constants the other side, and I have p over m, and an n, and an a, and this is going to have to equal to t to the 2n minus 1. Now the question is this a good guess? So I'm checking this guess all the way, and I want to say, is this equation satisfied? Now remember, this is not an equation which we're solving at one time. We want this equation to be true at all time. The thing about differential equations, you're not trying to find numbers, you're trying to find functions. And this equation doesn't just want quick satisfaction, it wants some long-term satisfaction. It wants to be true for all time, yeah? Shouldn't it be what? A squared. A squared. Okay, so we want this to be satisfied at not just one time, but all times. Let's say it was satisfied at one time. Then here's we've got a constant equals something. Now it's satisfied at another time. Now t's changed, and this whole thing has changed. So it can't be true at all times. Unless unless this thing is a constant. If we have a constant on the left-hand side, we have to have a constant on the right-hand side. Otherwise, they're not going to be equal to each other for all time. So this implies that t to the 2n minus 1 is equal to a constant. So we're fleshing out our guess. Now, is that possible that t to some power is a constant? If what? If 2n minus 1 is equal to 0. And that implies that n is equal to a half, which is that very good guess. But now we've taken a crude guess and made it into a good guess. So this looks like it's going to work out if n is a half. Now that n is a half, that says that a squared has to be equal to p over mn, but n is already a half, so a squared has to be p over 2p over m, or a is equal to the square root of 2p over m. And so that then tells us that we get a good guess, or a right guess, one that satisfies the differential equation, if we stick in that v is equal to the square root of 2p over m times t to the 1/2. What's funny about that?
I just unbelievably
Say again?
I just unbelievably, yeah, very impressed. I'm impressed.
What are you impressed with?
The scale.
But it didn't, it's not a bad, it's a reasonable kind of thing to guess, right? Now, let's just do it one more time, which is the way that they will try to teach you how to do it in the Math 293, which is not really the way that real people do things, which is the separation of variables. So this is a trick which works for some equations. And if you like, it's a different form of guessing, which is you guess that this is an equation of the type that you can solve with separation of variables. And so how does that work out? We have that p is equal to m times v times dv dt. And I'm just going to show you sort of some math manipulation. This is dv dt you can think of as a delta v divided by delta t. It says the velocity times the change in velocity by a change in time in small intervals in time. This thing has to always equal this. So we do this, it's a sloppy calculus. The mathematicians hate it, but it just works in engineering all the time, is you multiply both sides through by dt. And if you like, you can think about this in sort of the Riemann-Sem sense, that the power times an interval of time equals the mass times the velocity times the change in velocity. And you could sort of look at this, and I'm going to put a dt here, you can sort of look at this as the power equation. The net work is equal to the change in the net work is equal, this v dv is the change in v squared over 2. So the net work is the change in kinetic energy. So we're sort of deriving this conservation of energy thing here. But just looking at these symbols, we say it kind of looks like math. It would look more like math if we put an integral sign next to each of the things. And then we say, oh, I can do this integral. This one is p times t. This one is mv squared over 2. And then we have plus a constant, because when we do this integral, we're doing it as an indefinite integral. We have plus a constant. Now we add the boundary condition, or the initial condition, which was that at t equals 0, we get v is equal to 0. And if this is going to match at t equals 0 and v equals 0, that tells us that c is equal to 0. And then we get back this the same equation we have before, is that v is equal to, well, let's see, v squared is p t over 2pt over m, so v equals the square root of 2pt over m. So that's the separation of variables approach, which works in this problem, but it's really not as general or as useful as the guessing approach. Okay, everybody happy with these formulas? Okay, now we get to the next step, which is we want to plug in numbers. And now this next step of plugging in numbers is it's a ninth grade thing, but the fact of the matter is that people are very bad at this. So I want to try and teach you how to do this well. And it's a really boring thing, and everybody hates it when they get stuck with this situation. But what you have to do is like swallow this pill and say you're stuck being methodical. Plugging in numbers, especially when you're given weird units, is just a pain in the neck. And you all know how to fudge your way through, and what you'd like to do is be able to get your way through in a way that you feel confident and secure about it. So how are we going to do that? So here we have this problem that we have this t is equal to the square root of, what did I have here? I had it the other way around, right? I had v was equal to the square root of 2pt over m. Now this is v as a function of time. The problem that was given to you in your homework was to find time as a function of v. So we want to flip this thing around, and we want to say the time of interest is, now we get to square all this stuff, and we get v squared. This is the time as a function of v. T is v squared multiplied by m over 2p. So just to make a plot of this thing, we've got this v as a function of t, and it's going like this. And we know that we got up here to 20 miles per hour. And we're interested in, when we come down here, this is the thing we're trying to find. What's the t when this is 20 miles per hour? Okay, now we want to plug in this formula. We've been given all the numbers. So we want to plug in the numbers that we're given. And here is the answer. And this is correct. I'm going to write down something which is correct. It's 20 squared miles per hour squared times 150 pound mass divided by 2 horsepower. 2 times 0.5 horsepower. That is a correct answer to the question. How much time is it? It's 20 is 400 times 150, that's 600, 6,000, 60,000. It's the amount of time it takes to do this is 60,000 miles squared pound mass per hour squared horsepower. That is a unit of time if I've done things correct, and that's correct answer. So you can just answer, this is right. The answer is 60,000 miles squared pound mass per horsepower hour. Now, it's not a unit of time that you're familiar with, but it is a unit of time. Now, you'd like to turn that into a unit of time you're familiar with. So just that thing I just said right there, by the way, I think most of you don't know that. So let me just emphasize that. This is a correct answer in every way, it's just that it's not familiar. That is the amount of time. Assuming I didn't make an algebra mistake, but no one's pointed one out, so I probably didn't. Yes? Say again? Say again? I cannot hear you. Just yell much louder.
You don't want us to simplify the answer?
I do want you to simplify the answer. I'm just trying to tell you this is correct. It's not simplified. You don't get full credit for it. So the question is, how do you go about simplifying an answer like this? And there is a way to do this systematically. And the systematic approach goes like this. We have 20 times 150 divided by 1, which is just 1, and we have still left over here a miles per hour squared, and we have a pound mass, and we have a horsepower. So I'll just put a 1 over horsepower here. So here's our answer. 20 squared. The method is the following. It is always correct to take an expression and multiply it by 1. It does not change it. So what you do is you multiply this by 1. And you multiply it by 1 over and over again as many times as you like. And so long as you've multiplied by 1, you have not made a mistake and your answer is still correct. And what you do, again, is this method of guessing. You keep multiplying by 1, always having the right answer, until things cancel away that you like. So my goal is to get over here seconds. So I'm going to multiply by 1 in such a way that everything cancels except for seconds. And so how do I do that? Well, let's just start out with one value of the value 1 is 1 hour divided by 3,600 seconds. That thing is 1. So if I multiply by 1 like that, then everything is good. It's still a true expression. And I can put here raised to the 7th power, and it's still a good expression. Not useful, however. If I want it to be useful, I put here a 2, because then this hour squared is going to cancel that hour squared. Okay, so I multiply by 1, I haven't changed anything. What other 1 can I multiply this by? Pound mass doesn't look like a very nice thing. I don't like pound mass, so I put here 1. 1 kilogram divided by 2.2 pound mass is another way to write the number 1. And that's going to work out good for us because we're moving closer to SI. What's another one that's going to work out good for us? 1 horsepower is 746 watts. That's going to work out good for us because we got rid of the horsepower and we got it in watts. Now what's another way to write the number 1? Well, what's 1 watt? 1 watt is what happens when we take 1 kilogram and accelerate it 1 meter per second squared, and we do that for a meter, so we get a meter squared there. Now I've multiplied by 1 again. Now, if I've done the right things, if I've done the wrong things, I'll still have a right answer. It'll be just right and weird, like this was right and weird. But if I've done good things, then it will be right and not weird. So let's see if I've done good things and made it right and not weird. I have an hour squared cancels an hour squared. I have a mile squared. I didn't get rid of my mile squared, right? So I've forgotten the miles. So what do I have to do is I have to convert miles to meters somehow or other. So I have 1,600 meters is 1 mile. And that thing is going to be squared, so I've got to put a squared here. Now, who knows this number? Who doesn't know this number? Who knows 440? In track, they run 440s, right? 440? You ever hear of 440? What? I know, but they run 440s, right? That's meant to be what? A quarter of a mile, right? But in the SI world, they run 400s. Or a yard is like 10% less than a meter. So 400 meters is a quarter of a mile, so 1,600 meters is a mile. And if you don't know that one, you should know some way of getting back and forth between meters and miles. Okay, now let's go through this. We've got this mile squared, cancels this mile squared. We've got a pound mass over here, and it cancels the pound mass over here. We've got a horsepower over here, that cancels the horsepower over here. We've got a watt over here, that cancels the watt over here. We have a meter squared down here, that cancels the meter squared over here. We've got a second squared up here, and we've got a seconds down here, and what are we left with then is a second. Meanwhile, we've canceled. What?
That's second squared.
This one is second squared. What? Say again? cubed down here? Because a watt is a kilogram meter per second. Thank you. Very good. So then we're left with this whole thing, which says then that T is equal to 20 squared times 150, and then we have divided by 3600, divided by 2.2, divided by 746, multiplied by 1600, and this whole thing is seconds. So we got our answer here. Seconds. Yes? What did I do wrong?
You dropped the square at 1600.
I dropped the squared on 1600. This one gets squared? 1600. Bottom right gets squared. Any other mistakes? 3600 was squared too? Okay. So I didn't get to my MATLAB version of this, but we'll do this next time. Who did this problem not by getting a formula and plugging it in, but by integrating forward in MATLAB? Did anybody do that? Okay, so I'll just tell you what I'm going to do next time is, overall, my goal for this class is I want you to get in this MacGyver frame of mind. Whatever tools that are around, you're going to use them. So we're going to pretend that this math I did was over your head. We got to scrap it out by just figuring out little things to do in MATLAB to get an answer. And that's the way I do this. Take your homework, pass it to the end of the row.